Hello students and welcome back to study room. So today, as I told you, we're going to start the electric generator. So one thing that I want to tell you is if you feel scared of the two concepts, electric motor and electric generator, I would tell you that there is absolutely nothing to be scared of if you go step by step. Everything I tell you, everything you learn in each and every video would be used finally in the last concepts. So we took it step by step. We learned how an electric current gives rise to a magnetic field. Then we learned about the different loops and solenoids that give rise to a magnetic field when current is passed through them. We learned about the Fleming's left hand rule and we use that for the electric generator. Now, sorry. We learned the Fleming's left hand rule and we use that for the electric motor. Now, in the last class, I told you about Fleming's right hand rule and about electromagnetic induction. Now, keeping those two concepts in mind, now we're going to study the electric generator. This is the reason I always tell you to come prepared with the last topics you did, because everything that we have used in the classes before this is going to be applied in what we are studying now. Okay, so let's start with the electric generator. So the electric generator, just look at the words electric generator. What does that mean? Something that generates electricity, right? The electric motor was like what was powering different, which was the appliance which was powering different electrical appliances like the fan. The fan is doing mechanical work, right? The fan is actually moving, so there is mechanical energy being used there. So that is why for a fan we needed something that converts electricity to mechanical energy or electrical energy to mechanical energy, which was the motor. Now the generator is the exact opposite of that. Because we want electricity to be generated, we will use the electric generator, which uses mechanical energy and changes it to electrical energy. So it's exactly the opposite of what the electric motor is doing. Okay, now keeping all that in mind, let's move forward. So we're going to see what an electric generator actually looks like. So I don't know if any one of you has seen a generator in real life. If any one of you lives in apartments and that apartment has a common generator, you must have seen it. It's a huge generator, right? So anywhere, anytime that there is a power cut or the light is gone, that generator is switched on and it powers the whole apartment's electricity, right? So what is it doing? It is producing electrical energy. It is giving you electricity. That is why we call it a electrical generator. It's generating electricity. Okay, so the question is here, do you know the other name for this? Well, I will tell you if you don't know it. The other name for an electric generator is dynamo. Okay, this is the alternate name for an electric generator. Okay, just an additional bit of information for you. That was just an additional piece of information for you. Okay, now we're going to see what an electrical generator is or what is the principle that it works on. So an electrical generator is a device that converts mechanical energy into electrical energy, which I told you is the exact opposite of what a electrical motor does, right? Then it says that the electric generator works on the principle of electromagnetic induction. Now, what does electromagnetic induction mean? Do you remember what we did last time? We saw that magnetic field changing in a coil can give rise to a current. So that is what we are going to do. We are going to see do you remember what we did in the motor? So why I am again and again telling you to connect it to the motor? Because whatever we did in the motor, we are doing the exact opposite of that. So in the motor, we converted electrical energy to mechanical energy. In a generator, we're converting mechanical energy to electrical energy. In motor, we passed current through a coil. Ourselves, we passed a current through a coil and we saw the force that that current carrying coil experienced when it was kept in a magnetic field. But in a generator, what we are doing, we are putting that coil in an external magnetic field, but we are not passing current through it. We are doing the rotation bit of it. In the motor, that rotation bit was what happened because of the force due to Fleming's left hand rule. But in electric generator, what we are doing is we are rotating it and we are seeing what the direction of current is. So all three things are different. There is a magnetic field, there is a current, and there is a force. But what you have to remember is, in motor, because we are converting electrical to mechanical energy, so obviously the electrical energy we are providing, so current we are flowing and the force is experienced by it. That is why the coil turns and the mechanical energy is generated. In the generator, we said that we do exactly the opposite of that. That means we convert mechanical energy to electrical energy. So what does mechanical energy mean? Whenever we are saying something mechanical or something that has to do with mechanics, is always means that there is something that is moving. So in this case, can you think of what we will be doing? The apparatus is the same, well, almost the same, just one small thing is different, but the coil is there, the two ends of the horseshoe magnet, so to say, are there. So what do you think we'll be doing if we are providing the mechanical energy? What will we be doing? Will we be providing the current? No, because current means electrical energy, so we have to generate that, we don't have to give that. What we will be doing is we will be externally rotating that coil, because we are giving the mechanical energy, so we are moving that coil using mechanical energy, and then because of that movement, electrical energy or current will be generated. Okay, so that is the principle of electromagnetic induction that we saw, right? We saw that because when a conductor or a wire moves in a magnetic field, or the magnetic field related to it changes, that is when current is induced in the coil. Okay, let's go. So the components of an electrical generator. So it says that an electrical generator consists of a rotating rectangular coil ABCD, which is the same. This is the same coil like you had in case of your motor. It is placed between two poles of a permanent magnet. This could be a horseshoe magnet like this. This could be the magnet, right? So I'm not showing it here right now. This is just for you to imagine that this is not like two poles individually you have kept. This is actually connected. These poles belong to one magnet. Okay. Then these two ends of these coils are connected to two rings. Now, what is different here is, do you remember in case of a motor we had the split rings P and Q, but here we don't have split rings. We have full rings. This R1, this R1 and this R2, they are complete rings like this. They are complete rings, right? And they are inserted over this non-conducting cylindrical roll type of thing. Can you see that this gray colored cylindrical roll, this is non-conducting, and the rings are basically inserted on it. Think about like bangles being put on that cylindrical piece of non-conducting material, right? So these rings are inserted, and then these brushes B1 and B2 do the work of the X and Y stationary brushes. Okay, so that is why I was constantly relating it to the electric motor, because I don't want the electric generator to be a completely new thing for you. You should be able to relate it to the things that we have already done. Like, okay, there is the two poles of a magnet, there is a coil ABCD, there are two rings. That is what is different. Instead of split rings, there are two full rings. R1 and R2 are the full rings. Then the stationary brushes in case of the motor, which were X and Y connected to the two half rings, in this case are B1 and B2 connected to the rings R1 and R2. So like this, you can connect everything to what you have originally studied or you have already studied in case of a motor. So it wouldn't seem like too much work for you to remember these two things separately. Okay. So again, these two rings R1 and R2 are insulated on the inside. You remember we had insulated the half rings on the inside also, so that there is no current that flows between them. Insulated on the inside. Okay. So then these ends of the ring of the coil ABCD. This is the coil, right? A, B, C and D. This is the coil. This is the magnet between which the coil is placed, North Pole and South Pole. Again, it is these AB and CD arms are perpendicular to the magnetic field lines. How? The magnetic field lines go like this from north to south. So they are at 90 degree. We have already seen this, so I'm not explaining it all over again. I just reminded you about it. Okay, great. Now, the next thing is these two ends. What are they connected to? They are each connected to one ring. So say this is the ring R1 and this is the ring R2. I have not drawn that cylindrical object. You can draw it like this. This is the cylindrical object on which the ring is put. So one end, this end is connected to one of the rings. Then this end is connected to the other ring. Okay, this end is not connected to the first ring R1. Okay, R1 and R2. And this is R1 and this is the, and this here is the brush B1, which is the stationary brush. The stationary brush which does the work of the ring X, and the stationary brushes which do the work of the X and Y in case of the motor. You remember those stationary brushes. So ring R1 and brush B1 and ring R2 and brush B2. Okay, so the coil ends are not connected to the brushes because the brushes are stationary, but the coil has to rotate. So if the brushes are stationary and the ends of the coil are connected to the brushes, would the coil be able to rotate? No, because the brush is fixed. So the ends of the coil are connected to the rings R1 and R2, just like the ends of the coil were connected to the half rings P and Q, which could move. Okay, and then this B1 and B2 are connected to, this is a mistake in this figure, there is no battery. Why is there no battery here? Who can tell me why there is no battery? Because that is the whole point of a generator. We want to generate that electricity. We don't want that electricity to be supplied to us from outside. We want to generate that electricity. So why would we put a battery? If we already have a battery, then we have electricity and current. Why would we use a generator then, right? So this is not a battery here. There is a galvanometer here which detects which direction the current is going in, or which detects if current is being generated. Okay, so now we know all of the parts of the generator. ABCD is the coil, obviously the two poles of the magnet. The ends of the coil ABCD are connected to the rings R1 and R2, which are free to move on that cylindrical axle, right? This is known as the axle, you know. Axle is basically that object on which rotation can happen. So the rings can rotate because they are attached to this movable axle, right? And the brushes B1 and B2, which are stationary, and this B1 and B2 are conducting brushes. So that is what the wires are connected to. Okay, why are the wires not connected to the ring only? Why are the brushes needed? Because the rings are moving. The rings are going to be moving because we want to move the coil, right? So think about, if a wire is connected to the ring, as soon as the ring moves, the wire is going to go, there and then come down. It's going to all get entangled. That is why we want the wire to be stationary, right? So we want something that is in its place which we can attach the wire to, and we want something moving which we would attach the coil to, because the coil has to rotate. Okay, so I hope all of this is clear now, and now we can go to the working of the electrical generator. Okay, let's go. So there are still the components. This is what I explained it to you, that the conducting stationary brushes are kept pressed separately to the rings. Okay, so R1 ring has B1 brush connected to it, R2 ring has B2 stationary brush connected to it, and the brushes are connected to the galvanometer. See, it's written galvanometer here, but it's actually drawn as a battery, but this is a galvanometer. Okay, great. Let's go now. We're going to study the working of an electrical generator. So what happens is, again, this is a galvanometer. Please make these corrections. I'm sure it makes sense to you now, because we want to generate electricity. So why would we need a battery which already generates electricity, right? It doesn't make sense. Okay, now go with me step by step and everything would make sense to you. What you need to keep in mind is the Fleming's left hand rule. What was it? Quickly revise it with me. Thumb. This was the force in the left hand rule, right? So this time, is it not force, but we call it the movement of the conductor, because we are dealing with a moving conductor in a magnetic field. Okay, so we have basically just modified the left hand rule. It's not like we have changed the meanings of any of the fingers. This was force, This is also force or movement of the conductor. This was magnetic field. This is also magnetic field. This was current, and this is induced current. So we have just modified it according to what we need now. Okay, great. So left hand rule, sorry. Okay, so right hand rule, movement of the conductor, index finger, direction of the magnetic field, and middle finger, direction of induced current. So now you are going to tell me what we are going to do. I have already told you this. We want to generate electrical energy from mechanical energy. That means mechanical energy we are providing. Mechanical energy means anything to do with movement. So we are going to provide the movement. What are we going to move here? The poles? No. What are we going to move here? The coil A, B, C, D. Right? So what we do here is we move the axle so that the coil moves clockwise. What does clockwise means? That this arm AB goes upwards and this arm CD goes downwards. Okay. So the coil moves like this. CD goes down and AB goes up. Now we use Fleming's left hand rule. Okay, so the coil rotates clockwise. That means CD goes down and AB goes up. Now we use Fleming's right hand rule. Okay, what do we have here? We have movement of conductor because we have moved the conductor. And right now I am looking at this arm AB. Okay, which direction is AB moving in? Upwards. So my thumb is upwards. Awesome. What else do we know? Do we know the current right now? No, the current we have to actually calculate. So just don't look at the arrows that show the current right now. We will get to it. Okay, that is not given to us. Okay, the current is my middle finger, right? So I will not use my, no, the current is my middle finger. So I want to find which direction my middle finger points in. So I know my thumb is the direction of movement of conductor. I have kept it like this. My index finger is the direction of magnetic field and this is the current. Okay, magnetic field is in which direction? This direction? No, north to south. So it is in this direction. So I can see that my middle finger is pointing away from me. So that means current flows from A to B, away from me. A is near me and B is away from me. So it flows like that. Awesome. So let's write that down. So we write first point. Okay, let's write what we are actually doing. When we rotate the coil, I hope this is clear to you why we are rotating the coil, because we are providing the mechanical energy and we want to generate electrical energy. So that's why we are moving the coil. When we rotate A, B, C, D clockwise using Fleming's left hand rule, using Fleming's right hand rule, I keep saying left hand, please don't get confused. Right hand rule, we can see. So we have the case 1. Case 1, what's the first thing that happens? We see that current flows in arm AB from A to D. This is the direction of current. Now we know, because current obviously goes and comes back like this, but we still want to find the direction of current in CD, even though we know logically that is going to be from C to D, but we will still show that we use the Fleming's right hand rule to calculate it. So next, again, we know that CD is being moved in a way, CD is going down because the coil is going clockwise, right? So AB goes up, CD goes down. Okay, so thumb points down, movement of conductor is down. Then magnetic field, which direction is magnetic field in? Like this. Now I open my middle finger. So where is my middle finger pointing? It is coming towards me. That means current flows towards me. That means from C to D. So then we know that current flows in arm CD from C to D. Great. We are done with our case 1. Now case 2, what happens? What happens now is that the coil moves once clockwise. Now let us just quickly draw what the circuit would look like after this rotation. This is north, this is my south pole. Now after this rotation, the arm CD comes to this side, right? The ring doesn't move back and forth. The ring R1 and R2 can't exchange themselves. They can't exchange the positions, but they can just rotate and move in the other direction. So now if you can see, you have to visualize this a little bit. Okay, so CD comes to this side, right? So my coil is a little bit like this. Okay, pardon the shape of the coil. It is DC is here, D, C and B and A. This is the shape of my coil now. Now I know AB is what is connected to R1. So my R1 is here and AB is connected to R1, and this is still the brush B1, and this CD is connected to R2. This is R1. So CD comes from here and it is connected to R2 like this, and this is the brush B2. So my circuit looks a little bit like this now. This is my insulating, and the brushes are connected to the galvanometer, right? So I hope even if the figure is a little messy, you can understand what is happening, that the coil after one rotation looks a little bit like this. Okay. Now what happens is, we are providing the mechanical energy in the same way. So in the last case, we rotated the coil clockwise. Now also we will rotate the coil clockwise only. That means now this arm goes up. That means CD goes up and BA goes down. Again, now this time we will do it first on this arm. We do it first on CD. Okay. Again, you do Fleming's right hand rule. I am moving the conductor upwards. My magnetic field is like this. So my current flows like this. That means away from me. That means from D to C. So I write that current flows in arm CD from D to C, right? Now, interestingly, you can see that in first case, the current was flowing from C to D. Now it is from D to C. Okay, I'm going to tell you something very interesting about this. Now, if I look at AB, again, Fleming's left hand rule, AB thumb is downwards. Magnetic field is like this. So, when I hold my middle finger perpendicular to them, I see that the current is towards me. That means from B to A. Then again, we write current. You can write whole sentences, okay? You write using Fleming's left hand rule. We see that current in arm AB is from B to A, right? Now, what is interesting to note here is that the direction of current is reversed. Can you see that it has been reversed? First, it was flowing from A to B. Then after that, half a cycle, it flows from B to A. And first, it was C to D. Then after half the cycle, it was from D to C. So, current in each of the arms has reversed, right? So, we write that the direction of current is reversed in each arm after half a rotation, right? So this property is known as an alternating current produced. Okay, so this alternating current means which basically changes its direction after every half cycle. Okay, so we've written direction of current is reversed after half a rotation. Therefore, this current generated is called alternating current, or AC as a short form. Now, if we want to get a current that does not change its direction after every half turn, we use the split rings that we used in the motor. Okay. So when a split ring type commutator is used, we learned that the commutator is something that helps the flow of current, right? So when a split ring type commutator is used, then we get a current that does not change its direction after every half a cycle. So that current that is generated is known as a DC current. I'm writing it below the north pole, okay? DC or direct current. Okay, so the direct current is what is produced when a split ring type commutator is used so that the current does not change its direction after every half cycle. Okay, let's move on. Now, AC and DC generator, this is what I was telling you about. So, it says that a current which changes direction after equal intervals is called an alternating current. In the case of the generator that we studied, every half cycle current was changing the direction, right? We saw that was changing direction, and a current which does not change its direction is a DC current. It is a unidirectional current. Unidirectional means it only flows in one direction. Okay. The direct current always flows in one direction, whereas the alternating current reverses its direction periodically. Okay. Let's move on. Now, applications of an electrical generator. So these are the applications that you all see in your day-to-day lives, and you have this beautiful GIF running side by side where you can see all of the many uses of an electrical generator. Okay, so let's read. So the generators provide electrical power for day-to-day consumption because they convert that mechanical energy to the electrical energy which we need to get through our day. Okay, for routine power outages, this is what I said. Like in your apartments or any societies that you live in, you might have a common generator, right? So that generator basically, as soon as there is a power outage or the light is gone, that generator starts generating electricity. Used to charge batteries, used to run automobiles, aircraft, ships, and trains, for construction purposes, for mining, for fairs and carnivals, just to generate that electricity. Okay, and all of these points are actually shown to you in this beautiful GIF that is going on side by side. So please have a look at it too. Actually, very nice, right? Okay, let's move on. So, the first question says, state the principle of an electrical generator. So, we learned that the principle behind the electric generator is electromagnetic induction. Or the short form that we use is EMI, electromagnetic induction. But you will have to write this whole sentence, right? So if you can think, why does that relate to what we had studied in the Fleming's experiments, or the Michael Faraday experiments that we had studied, where we had a coil and a magnet. When we brought the magnet close, we saw current being generated. When we brought it far, we saw current being generated. Or when we had two coils, when we switched the key in, there was a quick current generated, and when we switched off the key, there was a quick current generated. So what was happening there? We said that the changing magnetic field around the conductor gives rise to a induced voltage, which gives rise to an induced current. So can you think, in the generator, how is the magnetic field around the conductor changing? That is because the conductor is being rotated in the magnetic field, right? So that angle that it makes with the magnetic field is continuously changing. That is how it is in relative motion, right? What did we say? That there has to be a relative motion between the magnet and the coil. Like we had said, either the coil has to be moved towards the magnet or the magnet has to be moved towards the coil. So in the generator, what are we doing? We have the magnets in one place. We are not moving the magnets, we are moving the coil. So when the coil is rotated, that means there is some kind of relative motion between the magnet and the coil. So the magnet So there is some kind of relative motion between the magnet and the coil, which gives rise to an induced potential difference, which in turn gives rise to an induced current. So how do we explain this? We say, when the coil is rotated in the magnetic field, there is relative motion between magnet and coil, right? Then, using Fleming's right hand rule, Fleming's right hand rule, we see that an induced current is set up in the coil, which is due to the induced voltage. So obviously current cannot flow before there is a potential difference or a voltage difference, right? So if there is an induced current, that is actually because first an induced potential difference was set up in that coil. Okay, let's move on to the next question now. So the next question asks us, name some sources of direct current. Now, I just told you when we were doing the generator, I told you that in the case that we did, every half a revolution, the direction of current is changing. So it is an alternating current. But I told you when we put a split ring in place of the two full rings, we get a direct current. So in that case, we call that a DC generator. And do you remember when we used to normally do current electricity? What did we use in current electricity? That battery made up of cells, right? Did that cell produce an alternating current? When we were doing the resistors in series, resistors in parallel, did the current direction change automatically? No, right? It only changed when we changed the polarity of the battery, when we made it upside down. It didn't automatically change, right? So that means it gives a unidirectional current or a direct current. So what we call that battery is actually a dry cell. Dry cell or the battery. Okay. So these are some examples of direct current. Okay. And the next question asks us, what produces alternating current? So we know we just did it, an AC generator. That is what we saw in the first case of the generator, or we call it the dynamo. Right? And if you have not heard about it, hydroelectric power plants also actually produce your alternating current. Okay. Let's move on. So this question asks us to choose the correct option. Okay, will do. So the question is, a rectangular coil of copper wires is rotated in a magnetic field. Okay. The direction of the induced current changes once in each 2 revolutions, 1 revolution, half a revolution, or 1/4 revolution. So if you remember the wire that we had taken, it was also actually a rectangular wire, right? The rectangular coil, and it was also placed between the 2 magnetic poles, right? So if you remember, how many revolutions did it change its direction in? Once, first time it was A, B, C, D, right? When we rotated it like CD goes downwards and AB goes upwards, then what happens? The direction of current reverses. If you don't remember, just go back and watch it. So what happens? Has it come a full circle? So what happens there? AB moves up and CD moves down, right? And after that, the current reverses. So has it come a full circle? AB moves up, CD moves down, right? Right now, it hasn't come a full circle. CD has just gone half a rotation. When CD comes back to its original place, that is a full circle. That is a full revolution. So where does it change its direction? At half a revolution, just when CD and AB exchange places. So our correct answer is half a revolution. Okay.